Today we're going to look at unit circle computations. Now that we know how to measure angles in both radians and degrees, that's going to be possible. Unit circle computations are pretty much one of the two things you should really let sink deep into your little skulls, because they're one of the two, that and what the graphs of like sine and cosine look like are two of the most fundamental parts of trigonometry. Does that make sense? They are absolutely essential for everything that follows it. So what is the unit circle, first of all?
Circle.
It's a circle with how far?
1 unit.
1 unit out in all directions. It's centered on the origin. So it's like the most simple circle you can possibly imagine, pretty much. Does that make sense? What's crazy about it, and if you look in your textbook, is they'll have all these points along the edges, and they'll have all these points labeled, and there'll be square roots of 2 and square roots of 3 and 1s and negatives flying all over the place for God knows what reason. So we're going to look more at how those points actually come about tomorrow, I think. Today we're going to really not even use the circle. It's going to be in the back of our minds as we perform these computations. So there's different approaches to how to do unit circle computations. For instance, my wife teaches her trig classes to memorize that circle day 1, all of it, which actually isn't that hard. You might think it's an overwhelming task, but it's not that hard either. I think we're going to try to build it a little bit more organically, and then we'll eventually have it memorized as well. And then you'll have some options on how you can do problems and think about them, okay? So it all starts from thinking about a circle that is really simple, and for some reason, the reason that we're going to investigate right now, when you think about this circle, pretend it's going out in one unit in every direction. Hopefully it's a circle and not an egg, but you know, that's the way it goes sometimes. So for some reason, the points on the edge of this circle will allow us to perform trig computations, things like finding the sine of 45 degrees, which we already knew how to do that one, right? But I'm not sure if we knew how to do the sine of 135 degrees or the sine of 1020 degrees or anything like that yet. And we need to be able to do all those computations as well. They come up all over the place, okay? So that's the goal, is learning how to do computations like the ones I have there. How do you find the tangent of negative 5 pi over 4? What's the ratio? So that's the idea. So I think that something really fundamental with the unit circle allows this to happen. Okay? So I'm just going to draw kind of a random angle, and I'm going to draw it in the first quadrant so it's a nice acute angle and it's easy to think about. What's it called when I draw the angle with one side right here, guys? So I'm going to draw it there. That's the initial side, that's the terminal side, but since it's starting from this axis, we call this angle in standard position. Yeah. Okay, so let's give it a name, like theta. That's the angle that I drew. This works for any angle, this little argument I'm about to show you, and it's one of the most important derivations in math, basic math anyway. So I just drew kind of a random angle in the first quadrant. It looks like 70 degrees, whatever. This works for any angle. So what I'm going to do now is look at the reference triangles. So I'm going to drop this down like so. Okay? So the reference triangle, I want to figure out what sides it has. What do you guys think? For that triangle, which one of these sides do we know? Do we know the dashed side so far? Do we know that little side right there so far that stops right there? Or do we know this hypotenuse side? We know the hypotenuse. The hypotenuse is 1. Why is the hypotenuse 1? Because unit circle. Unit means 1, right? Because the radius of the unit circle is always 1. Okay, we got that. So what can we label these 2 points? I wanted to just do this in general for any point that lands on the circle out here, right? That's what I'm talking about. My wife has her kids memorize those all right away. She doesn't do it very differently than this. Well, if it's just a generic point, how can you label a generic point, you guys? Totally, you could just call it xy. Well, if that's the coordinates of that point, you should know how long this is then. How long is this?
1/4.
It's x long. How long is this? How tall? That's y tall. Okay. You're kind of like, well, duh, Mr. McGee, why are you even asking me these things? I think I'm asking you these things for a reason. Why don't we just, for that triangle, just for grins, let's take the cosine of theta and the sine of theta and the tangent of theta. You know. So there's the sine of theta, we'll do the cosine, we'll do all three of the basic ratios. So what do we get for our triangle that we have here for sine of theta? Y over 1, opposite over hypotenuse. Since it's just divided by 1, do you even really need to write it over 1? No. I mean, you can if you want to, but I don't think you even really need this one here. So then this one is adjacent over hypotenuse, x over 1. Again, do you really need the 1? Not really, I don't think so. And then tangent of theta would be opposite over adjacent. Y over x, you kind of need both those, I'm thinking. What's this really say? This says for any point, at least any point on the edge of our circle like this one, or if I move it over here, same thing will work. If I move it over into the second quadrant, I think the same thing will work, or the third quadrant, or the fourth quadrant, if I go around twice and look at coterminal angles. This says that x, y can be represented another way. How can any point on the unit circle be represented? And this is like the edge of really good math. Careful.
Oh, cosine. Sine.
Yeah. Any point on the edge of this circle can be represented as cosine of the angle that makes that point and sine of the angle that makes that point. And actually, if you go for circles that are not the unit circle, if you extend this to any other point, you know, because any other point in here would have a radius of less than 1, all you've got to do is change one little tiny thing in here and you have a totally new way to represent points. And this new way of representing points, what it will do for us today, it has lots and lots of other applications too. But what it's going to do for us today is let us perform little computations like finding the tangents of these things and stuff like that. Okay? It's a totally new way to represent points. Now instead of thinking x, y, we can think of cosine, sine. And this goes back to what I said when we started looking at trig ratios. I said cosine, yeah, it's adjacent over hypotenuse. But I said spatially, cosine is like adjacent over hypotenuse. Adjacent is like what coordinate? Look at my arm. Is that an x coordinate or y coordinate? It's an x coordinate. Cosine is intricately bound up with the idea of being horizontal. And sine is like a y coordinate. Sine is intricately bound up with being vertical. Okay, that's a really good idea to have. A big idea, big concept. Okay, so let's use this and actually start performing some computations. So remember, we've got sine is y, cosine is x, and tangent's the ratio of the two. So actually, this also proves an identity in trigonometry, which is tangent can be written as what else?
Sine, cosine.
Sine over cosine. If sine's y and cosine's x, then tangent's sine over cosine. That's a deep truth embedded in trigonometry. It's one of the first identity we've learned. Tangent is sine over cosine. Okay? All right, so let's do some computations. So how do you use this concept to do something like the tangent of negative 5 pi over 4? First, you want to draw the triangle. Exactly, you got it, Akash. You want to draw the reference triangle. How do you know where to draw the triangle for negative 5 pi over 4? This is where what we've been working on with radians starts to come into play. So you count by the denominator. You count by fourths. And we're counting forwards or backwards?
Backwards.
You're backwards from here, right? So in fourths, how many fourths does it take to go halfway? Forget about this for now. This is negative 1 pi, right? Negative 2 pi. So how many fourths fit into 1?
4.
4 fourths. This is negative 4 fourths. So where's negative 5 fourths?
1.
One more, right? So it's in the second quadrant, right down the middle. And then, you remember from yesterday, pi over 4, fourths. How many degrees was that? Was it 30, 60, or 45?
45.
It was 45. And then you say, hey, this is a 45, 45, 90 triangle. I know the sides of a 45, 45, 90 triangle. 1, 1, root 2. And then you look at that triangle and you're like, man, did I label that triangle right? Are all the coordinates good? No, one of them's not quite good. It's close. Root 2 is good. Which one? This guy is going to the left, so shouldn't it be negative? There you go. Now you've got your triangle, do tangent on it. So the tangent on it becomes opposite over adjacent, which is -1. Now I haven't really used this sine cosine thing of points yet, but I'm going to. Just wait. That really is just all prior knowledge assembled. All the stuff we've learned in trig so far pretty much went into that, didn't it? So let's do another one where we do need this idea of the unit circle to do it. 7 pi over 2. Let's use the same strategy. We're going to count. This time we're going to count by halves. We're going to count forward from here, right? So halves. There's 2 halves there to get 1 pi. So 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7 halves. This one doesn't make a triangle. It lands right on one of these edges. And if you're on the unit circle, what are the coordinates of this edge? Can you guys tell me? And be careful on this, because if you're like me, you'll mess it up every time if you don't think about it for a second. How far down did it go? 1 down. So which one of the coordinates should be -1?
The
Y. And the x is 0. Now I asked you for the sign of this spot. What's the sign of this spot? What is it, Mr. Garrick?
-1.
-1. Where's his -1 coming from?
Because sine is y.
Because sine is y. Sine's the y coordinate. Boom. Okay. And see, if we thought about this over here as the coordinates of this guy, which we could, then we could do it like that too, right? Like I could have thought about the coordinates of this guy from the triangle being -1, 1, and then doing y over x for that one too, but that was kind of extra work because we already know tangents opposite over adjacent, right? So there you go. Let's do 11 pi over 6. So 11 pi over 6. I'm going to scoot some of this out of the way. I'll do a little picture over here. So this time we're counting by sixths. How many sixths are halfway around the circle? 6 sixths, because this is 1. 1 is 6 sixths. All the way around would be 12 sixths. So I should go back 1.
Yep.
Back 1 sixth. 1/6 in radians, pi over 6. How many degrees was that from yesterday?
30.
It was 30 degrees. And then you say, oh yeah, that's a 30, 60, 90 triangle. I know that guy. I've met him before. Opposite 30 goes 1. Opposite, this is a 60, right? Goes root 3, and the hypotenuse has a 2. And you say, well, are all of those good over there in the 4th quadrant? I think one of them's negative. Which one? This one's negative. Now, some of you are telling me the 2 is negative. Not a bad idea. Think of the radius as like an absolute value. The hypotenuse is always going to be positive. It's just the distance from the origin. It doesn't have a negative or positiveness to it. This is left, right, which is positive, and this one is down, which is negative. Okay? You've got your triangle, you've done all the hard work, do secant. So for secant, I think of it as the partner of cosine. Cosine of this guy is adjacent hypotenuse. So scratch work. To get secant, I flip it. So that'd be a right answer. Or if you rationalize it, you're going to get rid of that root 3 by doing this. So a better answer would be that guy. Either one would be fine, the blue or the red. Okay, let's do a few more examples. All right, so more basic unit circle computations. Let's do 6 more. So cotangent of 225 degrees. This time we don't have like radians to count by, but I think the principle's the same. We need to figure out where 225 degrees is. Can you guys help me draw that? What quadrant? 225, more than 180, right? How much more than 180?
Just like quite a bit. 45.
45 degrees. So there's our reference triangle that we needed, right? So 45, 45, 90. Help me out. How's that go? Opposite the 45s, you go 1, 1.
Wait.
Square root of 2. Okay, then you look at it and you say, okay, something's wrong here.
That one on the side that's going
This
down.
one?
Yeah.
It's going down, okay.
Yeah. The one above too.
That one's to the left, so those are both negative. Very nice. Okay, once you've got your triangle drawn, doing the rest of it shouldn't be a big deal. It says cotangent. Tangent would be opposite, adjacent, so flip that. Yeah, I think you get the same thing on this one. There you go, done.
Oh, nice.
Cosine of 13 pi's. We should be counting by what then? There's no denominator, but you should be counting by ones, pi's, exactly. So let's think about this. I don't want to draw like a crazy diagram going around, but 13, where's it going to end up?
Over there.
It's going to end up on the left. You can, of course, count it and go 1, 2, 3, 4, 5, and then quickly you'll realize, oh, all the even pi's land here, and all the odd pi's land here. I think that's what they did. What's this coordinate? Be careful with your coordinates. You're going to mess up if you don't. Think every time in your head. X, Y, X, Y, X, Y. What's the X? -1. What's the Y?
0.
I'm telling you, if you don't do that, you're going to mess up. Cosine. How do you do cosine of a point on the edge of the unit circle? Cosine was the X. Done. Okay. Tangent of 3 pi over 2. We're counting by... Yeah, halves. Good. So halves. There's 2 halves here to make ones. That's 2 halves. So 3 halves is just 1 more half right here, right? That's one you should memorize, by the way. Where is 3 pi over 2? It'll serve you well, especially when we graph. 3 pi over 2 is here. We're going to think x, y, x, y, x, y, x. 0, y. -1. In my head, I'm always doing this and this. That way I don't mess up.
Y over X.
Y over x. But with a y, that is -1. The x of that is... You can't divide by 0. This is undefined. So can things be undefined in trig land? Yes, that must mean the graph of tangent has what? Think about what undefined meant on graphs we have seen. It did mean that sometimes. Very nice, Akash. It also meant asymptotes. You guys remember when we did rational functions and you divided by 0? Did we in fact plug things into the bottom to try to make it be 0 to find the asymptotes? What you're thinking with imaginary numbers is good too. That's interesting. This is an asymptote. Tangent has asymptotes. One of them's at 3 pi over 2. We'll see that soon. All right, 135 degrees. We don't have radians to count by. We just need to figure out where's that land. Second quadrant. All right. How much for the reference angle? It's over here, right? 135. What's 180 minus 135? Is it 45? I hope so, because otherwise we need a lot more math to do this unit circle computation. So you guys saw me as I was setting these up. I was thinking about them a little bit, so we didn't get one we couldn't do yet. You have to know a lot more trig to do something. Yeah, the worksheet of you're all good. Don't worry about it. Good question. So 45 over there. Oh, it's our friend the 45, 45, 90. This one's negative. Done. Cosecant goes with sine. So that way I like to do these is I just think of sine. So sine's opposite hypotenuse. So flip that. Hypotenuse opposite root 2 is the answer there. Okay. Let's see, sine, this time we're counting by sixths. We're going backwards because it's negative. So I'm going to go 6 sixths, 12 sixths, 18 sixths, 24, 30, 36 sixths. I went too far by 1, so it should be right there. So it's 1/6 back here. A sixth is how many degrees again? 30 degrees. Quick way to remember that. I think it's not the best way, but 3 goes to 6. 6 goes to 3. Yeah. 30 degrees, opposite gets 1. The 60-degree angle opposite that you get square root of 3, and a 2 goes on the hypotenuse from Pythagoras. Anything negative? Right, up, good. Sine is opposite hypotenuse. Done. Okay, this time we're counting by thirds. We're counting backwards again. So I'm going to say, how many thirds are right here?
1/3.
That's 1 pi, but in thirds, 1 pi is 3 pieces, 3 thirds. I need 4 thirds, so I'm going to have to go more here. Thirds are how many degrees? 60. Opposite 60 goes square root of 3. That means this is 30. Opposite it goes 1, and the hypotenuse is 2. Anything negative? 1 again. Secant goes with cosine. Cosine of this is adjacent to hypotenuse. Flip it, and you get negative 2. Okay, that's how you do unit circle computations.